Hi everyone, so welcome again to another video of Math Safety Ref. So for this video, I will discuss actually only numerical integration, but for the succeeding one, I will also discuss the numerical differentiation. Now for the outline, we have again numerical integration and differentiation. So for the numerical integration, we have the Newton's closed integration methods, which are the trapezoidal rule and Simpson's rule. We'll discuss this later. And then for the numerical differentials, we have backward, forward, etc. For difference. Okay. So for the intended learning outcomes, I'm not read this anymore, guys. Just view this in the PDF file. Let's begin with what is integration. So integration is basically just the area under the curve of a function with respect to its x-axis. Okay. So if you want to find the area between A and B, which is this and this, then enclosed by this curve and this x-axis, then you want to find the integral, or to be specific, the definite integral function, and then evaluate on these points A and B. So what we can do, the application first, the application of integration spans across a lot of engineering principles. So the simplest one that we have is the mean. So calculating the mean is actually finding the area. It is actually finding the area, but we usually deal with mean as a discrete value of discrete values of the data. But we can have a continuous version of this discrete data where this is the representation. So we have this curve pattern here. Okay, we have a similar approach with a continuous one. So to find the area of this, actually, if you find the area of this, which is just the sum, the sum of the y's here, and then dividing this by the total value of this, you can find the mean. So the mean here is dividing this total area by this width here, which is also n, and this will be your mean. Okay, and if we do that as well for a continuous function, you can find the area and then find the difference between these limits, and you will have computation of the mean, which is just the definite integral from b of fx over b minus a. So a and b are limits, which are constants. Limits. Now, how do we apply, or where do we apply integration? Or to be specific, just to simplify things, actually, we want to integration by parts here, or anything that we have discussed before. We will only solve the integral using numerical methods. So if we want to find, let's say, for example, the area of this region of the map, as you can see, you have this very neat, uh, very neat wide x-axis, and then you have this curvy pattern here, which can be described as a function of x, for example. But you can do this in discrete ways. So we have grid lines here. You find the area of this, find the area of this, find the area of this, and so on. And actually, what we did there is actually called the Riemann sum. No? And we can do this as well for hydrostatic pressures. So what does this mean? So your pressure here actually varies with height, right? So the deeper you go, the higher the pressure you will experience, as described by the law of hydrostatic pressure. And that will be the same as well for wind patterns. So the wind will be much faster, or it will give up more momentum or force versus the wind below. So you have a distribution of your wind. You can find the total distribution of this wind. You can have the average force interacting with this building. So you can imagine a building sometimes will wiggle if the force is fairly high or the wind is very high. It will wiggle for a little bit, we have this distribution of velocity of the air, wherein it will be the velocity will be higher at a uh, higher height. It's a lot of highs. No? So how do we do the numerical method of integration? So the general uh, formula that we will use is actually just the Newton-Cotes formula. And the Newton-Cotes formula basically just utilizes polynomials as its as an estimation of the function of the curve, and then find the area of this polynomial curve under this function. So if you want to find this integral, you can estimate this by, instead of having some nonlinear function, or we don't know the function, this should be x here, we can estimate this by f of n, which is an nth order n degree polynomial. This is actually degree n degree polynomial. So what does that mean? So let's have a very simple example. So we have trapezoidal rule. No? So the single trapezoidal rule, to be exact, there is actually a composite trapezoidal rule, which will be discussed later, is that we have a line. So we have a curve or a curve here. So basically a trapezoidal rule, let's say this is the limit. To find this area, you will have a linear interpolation and then find this area. So basically a trapezoid, as you can see. So we will do a linear interpolation of the curve and then find the area under this curve, and you have a numerical method, which is called the trapezoid. So how do we find this? So where did this came from? So this is actually your f of n, the function or the linear function f of 1, since this is just degree 1, no? So first degree polynomial equation, which is also a linear function. So as you can remember, no, maybe you can remember, what is this? This is b1, and this is just f of x1, right? And this is your f of x2, and then this will be f of x1. So you get the point here, right? So this is just linear interpolation, and then that's it. So if you evaluate actually this integral, it will be much easier. So instead of integrating some function, complicated function, you can do, or you can approximate this as a linear function and then integrate. So if you integrate this, you can integrate this independently. So I'll just skip to the, sorry, I will just skip a lot of shortcuts here, or I will skip a lot of steps here. So if you integrate this, just remember that anything as a, b, f of a, f of b, just remember that these are just constants. This is all you need to know to integrate this. So we only have one variable here, which is x and x minus a. So sorry, x, only x, but this is a function. X minus a. So if we integrate this from a to b, the integral of f of a will be x times f of a. Okay, I hope this makes sense. And then we have two terms. So how do we integrate this? So this will be actually, so since this is a constant, it will retain its form. So we have f of b minus f of a. And then we have b minus a. And then this will be just, the integral of x minus a is x minus a squared. So using the general power rule, and then over 2. Okay, so this should be evaluated from a to b. Okay, so now if we evaluate this, so let's substitute the value of b, not there, but this here, only here, and then here, and then also for a, and then here. So we have the integral, the approximate integral will be b times f of a, and then so on. So this. Okay, and then we have x minus a, so we have b minus a squared over 2, and then minus, so we have minus, I'll just write this down below, say this is here, so that we have a negative, we have to distribute this later. So we have a f of a plus f of b minus a, so copy and paste everything but we just have to change this x minus a into 3 minus a squared over 2. Okay, so as you can see here, we can actually cancel out the 0. So if it's 0, then all of this term is 0. So it simplifies into negative a f a, f of a. Now for this one as well, we can cancel this out. As you can see, we can cancel this, we can reduce an exponent by 1. So we, to simplify this, we have b of times f of a, and then we have plus we have f of p minus f of a, and then multiplied by b minus a over 2, and then we have minus a f of a. So if we simplify this, we have two like terms here. So we have b minus a f of a, as you can see, and then actually, uh, we can actually simplify this even further, right? So we can distribute the over 2 here. So we have plus f of b over 2 minus f of a over 2, and then that should be multiplied. Oh, sorry, right. What did I do here? Ah, sorry. Not yet, not yet. Okay, sige, never mind. We will discuss this later. Sige, let's write this down for now. A and then b minus a. And then over 2. Ayan, sorry. So as you can see, we have here a factor, a common factor. So we can factor out this common factor. We have here f of a. This might not make a lot of sense, but it's only because we write a lot of letters. So we can actually simplify this. So they are like terms. So basically 1 minus 1 half. So cancel this into. This will become f of a over 2. So that this will become b minus a, and then we have f of a plus f of b over 2. That's it. So this will be your integral, or actually your approximate integral will be this. So as you can see, this is also what it is. Okay. Okay. So there is the formula. So where did it come from? We use the linear interpolation of linear function, and then we have this formula. Now, how do we use this? Or how do we visualize this first? So if you have, let's say, a function, we want to find the area here. Actually, this was the area we're looking for. We can estimate this area by finding the linear interpolation between these 2 points and then solving for the area of this trapezoid. Basically, that's it. So, for example, here we have a function that we want to solve here. And we want to numerically integrate this. So how do we do this numerical integration? Okay, so to find the integral with regards to a single trapezoid, which is just the formula now b minus a, and then we have f of a plus f of b or over 2. So let's just do this, and then it's over. So how do we do this? Just substitute b, we substitute a, we substitute a, we substitute b. So what? So this is your function. So we just substitute a here, get this integral. So this will be b minus a, and we have 0.8 minus 0, okay, and then plus, sorry, not plus, but multiplied by f of b, sorry, f of a, which is 0, and then plus f of b. So f of b here is f of 0.8, and then all over 2, and that's it. So how do we solve for f of 0? So you just substitute 0 here. So if this is 0, 0, 0, so this will be just 0.2, no? So 0.8 times 0.2, and then plus, so substitute here the 0.8 value, guys. So substitute 0.8 here. I want to do the calculator anymore to save time. This will be just 0.232, and then all over 2. So if you simplify this, you will have an answer of 0.17. Okay? So if you compare this to the actual integral, compare this to the actual integral, I'm not integrating this anymore, but the actual integral, the exact value, we have an answer pala, no? We have an answer here. So it is very far, ano? And that is actually because we only use single or a single trapezoid. And to visualize, what do I mean by that? Is that this is your function, and you have two endpoints. So you have these two endpoints here from A to B. And since, as you can see here, if you connect these 2 points, then your integral estimate will be just this. So the error will be large if the function is highly nonlinear, and also if what do you call this? If we only use one single trapezoid. So we can actually use more than one trapezoid. We can divide the sections equally. So instead of just one trapezoid here or one four-sided shape, we can do something like this, and then this, and then this. So this is the composite trapezoid method. Now, for the composite trapezoid method, the estimation will be much better. So I won't show you the derivation anymore, but the formula will look like this. So remember this, guys. And it will look like this. So we have here x0, x1, x2, and x3, and so on. So as you can see, the estimation will be much better than just using a single trapezoid. So you have 1, 2, 3, 4, 5 trapezoids here, and it will yield a better estimation. So numerical methods is for estimation, so it will be better. So what does this mean? So this is basically just your first point, and this will be your last point. So everything in between, everything in between should be multiplied by 2. And then for the calculation of h, that is just basically b minus a over n. Usually, b, a, and n are specified. You just have to calculate this h. So let's go on and do this. So use two-segment trapezoidal grid as the integral of this with a similar function from a to b. So how do we do this now? The integral is equal to, we have h over 2, right? Right. Let's forget this. And then we have f of x0, and then plus the summation of, or sorry, 2 times the summation of f of xi, I is equal to 1 up to n minus 1, and okay, so what is h? So we can calculate h first. So h is just b minus a over n. So we have 0.8 as b, and then 0.0 as a. And then n here, if we say 2 segment, basically n is equal to 2. So we have 2. So this h will be equal to 0.4. Okay, so we have h here. We're good with h. Now, how do we solve for this? So we have f of x0 and so on. So we just have to tabulate everything. So if we have two-segment trapezoidal rule, if you visualize this, guys, you have to visualize this first off. So if you have your, let's say your function, imaginary function, we don't know the function. Actually, we know the function. I won't know the function anymore. So if this is your 0, this is your 0.8. We want to create two segments. So basically two trapezoids. So we can imagine there should be a 3-point here. So that we have this first trapezoid. And then this will be your second trapezoid. So first and second trapezoid. So to find this third point, we want to use the h. So the h here, the purpose of h here is to add this h so that this will be just delta h. Or sorry, the difference here is just h. The difference here is h. So we have here, this point here should be 0.4. So therefore, if you tabulate this data for x versus f of x, if x is equal to 0, then we have a value of, actually we solved this one already. So if you substitute 0 here, we have 0.2. Okay, substitute 0 here. Okay, just remember this. So everything will cancel out. We have 0.2. If we substitute 0.4, which is also our x2, so we have x1 here, x2. So if you substitute 0.4 here, so I won't show you the answer anymore. Sorry, the calculation anymore, but x2 will be, or f of x2 will be 2.4. Is it 2.3? Okay, 2.456. 2.456. And then we have 0.8. So 0.8, we already know this as well from the last problem. So this will be your x3. This will be your f of x1, f of x2, and so on. It depends on you. You can also notate this as 0, 1, 2, or 1, 2, 3. It depends on you. But the formula is actually f of x sub 0. No? So, actually, this is just x sub 1. So the first one is this, and the last one is this. So basically, to use the formula, we have I is equal to h over 2. So we have 0.4 over 2. Okay? Multiplied by f of x sub 0. So this is just the first one. So the first one is 0.2. So yes, this. And then multiply everything in between. So if we have more than one unit here, or we have more than one data point here, you will just have to multiply this by 2. And then you just add the value of f of x. So we have 2.456 here, and then plus 0.23. Okay. So that's it. So just calculate this, and you will have an answer of, let's check this. You will have an answer of 0. Sorry, not 0, but 1.0688. Okay. So the actual area is 1.6405. So it is better than the previous one. And if you visualize that, okay, so if you visualize the area that we found, it will look something like this. Okay. So instead of just doing this, right, we can do this. We can have two segments so that we can find the area and then we solve for a better approximation. We can do even three segments if you want. We can have this 3 segments. So this will be an even better approximation and so on. So if you increase n, the line segments, sorry, the segments, then the approximation will be much better. So if you visualize this, for example, you increase the n, and you compare this integral, it will get closer and closer to the actual value. So the approximate error, sorry, the true error, relative true error will be lower. So if you visualize, let's say n is equal to 10, you have n trapezoids, then as you can see, the area will be closer. We have a smaller error here compared to the last one. Okay? So better approximation for n for greater n or higher n. Okay. Okay, so I think that's it for trapezoidal rule. So you can have n is equal to 3, 4, and so on. Let's now move on and the next method, which is the Simpson's rule. So for the Simpson's rule, basically the Simpson's rule is just a quadratic and a cubic approximation. Okay, so what do you mean by that? So this is just a quadratic function. You can imagine this is a quadratic function, and this is your cubic function. So as you can see, if you have this function here, it will approximate this function by a quadratic function here. Okay, and then if you are going to use the other Simpson's rule, which is a 3-8 rule, it will be a cubic function. Okay, so the 3-8 and the 1/3 rule. This is just the quadratic approximation or the quadratic function, approximation of the function. And then this would be the cubic. Okay. So the first one is just a linear. We have quadratic, we have cubic. So for the 1/3 rule, we have this formula. So this is single. This is a single Simpson's 1/3 rule. And then for the single Simpson's 3 rule, we have this. Okay. So for the Simpson's 1/3 rule, you need at least 3 data points. For Simpson's 3 rule, you need at least 4 data points. Remember that as well. Okay. So let's move on and let's solve already. First example here. So to solve for this Simpson's 1/3 rule, again, this is just basically quadratic approximation of the function and then find the area of this quadratic function. Now, to solve for this one, we can do here is we have the formula. The formula is the sort of body here in numerical methods. So we have what is this? We have 8 over each over 3. So I'm cheating now. I'm cheating and looking into this formula because I do not remember this. Okay. So for f of x1 and then f plus f of x2. Now, Simpson's one-third rule, we need at least 3 points. So what should we do here? You have to divide the points into actually two segments. So why is that? So if you imagine also, if you have this, let's say this function, so if let's say this is your first point, and let's say this is your this is second point. Okay, so we have this x and y axis. So to find this quadratic function, you will need at least 3 points, right? So you have to do this. So the approximation of this point will look something like this. Okay. So you can find this area, and this will be your approximate area. So you need at least 3 points. So you need to divide the segments by 2. So the n here will be just 2 for Simpson's one-third rule. So to find h here, this will be equal to b minus a over 2, which is equal to we have b minus a, we have 0.8 minus a, so 0 over 2, which is actually just 0.4. So basically, you have 0 here, and then the next point here is just the difference h. So this will be 0.4, and then the point here will be 0.8. So using the formula and tabulating the values, actually we already solved for this one. So x and f of x. So if this is 0, we have 0.2. If this is 0.4, this is 2.456. We already solved for this. We have already solved for this. That's this problem. And then we have 0.232. Okay, so that's it. Now we can just substitute the values. So this is your f of x0. This will be your f of x1, so the between, and then the last term. So you have h over 3. So the integration, or using the Simpson's rule, will be h over 3. So 0.4 over 3. And then f of x0. So 0.2 plus 4 f of x1. So we have 2.456. And then plus 0.222. Okay, so the integral or the approximate integral will be 1.365. So this will be approximate area. Now the true area is 1.6405. So the difference is much smaller than the previous approximation. So you can see now how do you visualize this Simpson's one-third rule. We don't have pala, no? We don't have a visualization. Okay, anyways. Where are we? Show slideshow. Okay. What happened? Okay. So for the Simpson's street rule, let's say for the similar example, so for the three rule again, for if we're talking about three rule, it is just the cubic approximation of the function and then find the area under the curve of the cubic function. So the formula for Simpson's street rule is h over 6. We should look at 3 over 8 pala. Okay. So we have 3h over 8, and then you have f of x sub 0 plus 3 f of x sub 1. So f of x sub 3. So as you can see now, the middle terms are multiplied by 3. So remember that. Okay, so what about h here? So the h here is what? So if this is a Simpson's street rule, a single Simpson's street rule. So if you have, let's say, a function example here, for example, function here, we will need at least 3 points. sorry, 3 segments. Since this is a cubic, we need 3 segments to approximate. This will be 4 points pa rin. So 4 points, so it should be equally spaced. So the difference between this and this and this should be just h. So therefore, if this is 0, then this will be 0.8. Then the in-between should be h is equal to b minus a over 3. So remember that this should be 3. So this will be 0.8 minus 0, 3. So h here will be different from the previous one. H will be, what is this? I cannot divide this. So we have 0.8 over 0.7. So 0.267. So this point here is 0.2667. And then if we add another one, so basically if this h, then this will be 2h. So multiply the h by 2. So times 0.533. 0.5333. Okay. So how do we now do this? So again, tabulate your values to make things organized. So again, we have 0 here, 0, and then we have 0.2. We're going to solve that. And we have 0.2667. You solve this later. 0.5333. And then 0.8. So 0.8, we have a value for that as well. That is 0.222. So sorry, I will not substitute the values, but if you substitute the value of 0.2667, you will have a value of 1.4327. And then for this one, for substitute 0.533, you have 3.4872. Okay, now we will just substitute the formula. So basically, this is the first term and this is the last term. So this is the first term, this is the last term. And then we will only multiply this by 3. So therefore, your integral here is equal to 3 times h. So h here is 0.26. I forgot to write this down. So 3 times 0.2667 over 8. And then multiply this by 0.2 plus 3 times. So a neat thing here is that you can just group them now. So you can factor out the 3 here. And then you can just add f of x1 and f of x2. So you have 1.4327 plus 3.4872. And then you can add also 0.228. So the integral here will be equal to, I will not use the calculator anymore. Yeah, 1.5192. So somewhere along this range, you have this integral. Now, as you can see, this is a better integral or a better approximation of your. Now, we can make this even better. So this is just a single application of the Simpson's rule for 138. Now, if we do a composite one, okay. So if you do the composite rule, we will have something like this. Okay, this is the last slide. So for the 1/3 rule, so basically we are trying to what do you call this? What is that word? I can't find the word for that. So this is the first simple Simpson's 1/3 rule. This is the second Simpson's 1/3 rule, third Simpson's 1/3 rule, and so on. As you can see, there is a repetitive of this 1 for 1. You can remember you have this coefficient 1 for 1. And then since we have intersection here with 2 ones, we can just add them up and we will have 2 here. So therefore, the formula here is to sum all the actually this should be the equation if we will use x1. So it depends on you. It will be this formula plus 4, and then you have summation of xi, and then plus 2 summation of fxi or fxj, and then plus f of xi. So usually, the book tells us to start with 0, but I usually start with 1. So depending on the case, it should alternate in between. If you use x as 0 sub 0, then the values of f of x should be multiplied by 4 if it is an odd number. If it is an even number, multiplied by 2. But this will be interchanged actually. The 4 will be multiplied by the even number actually. If we use x1, this will be even numbers, this will be odd numbers of xi and x3. Okay, let me just show you what I mean by that. So again, the same problem, and then we will use an n of 4. So how do we do that now? So for the, I'll just show you the formula here later. I will try this down in order. So for this formula to work, we need to know the h, right? So we need to know the h, which is equal to b minus a over n. So n is given as 4. So we have 0.8 minus 0 over 4. So this will be 0.2, right? So we are good with h. Now, how do we solve for the other values? So if we have n is equal to 4, so remember that if n is equal to 4, that means we have 4. So we have 4 rectangles now. But basically, we need to have 5 points. So we already have the first point and the last point. We need to fill in 2 points to make it 4. So to find the other points, we can just tabulate here directly. X versus fx. So xi and fxi, or x and fx. So we have the first point 0, and then the second point here will be a difference of 0.2. So 0 plus 0.2, we have 0.2 here. Another difference of 0.2, we have 0.4 until it reaches. Sorry. What did I do? Zero. We need 5 points for that. We need 5 points. And then 0.8 pa yan. Okay, so for this, we know that this is 0.2, with this 0.222, 0.2 and 0.4. We already solve for that, right? Only 0.4. So we have 2.456. Should I have my notes here. So 1.288. And then we have 3.464. So how do we solve for this again? You just substitute the value of 0.2 here. Okay. Substitute value of 0.2 here, you will get 1.23 and so on. Okay, so for the formula to work, again, I is just h over 3 multiplied by the first term. So remember that this is just the first term. So f of x of 0. And then the second, multiply this by 4. So after the first term, we will multiply the second term by 4. And all of it summation alternating in between. So we have here 4, and then actually this will be x1, and sorry, x1, but f(x1), f of x1, okay, plus f of x3, since we have terms there, and then we have 2 times f of x2, and then plus f of x4. So we do not have an x4, no? So if the last term is f of x4, so we do not need to multiply that by 2. So remember that, ano? Yes. So how did we come up with this? So if we use this as our reference, x of 0 is x of 1, x of 2, x of 3. So we use a different notation, no? Instead of 1, or instead of starting from 1, we started from 0. So the last term will be this. So the last term should always not multiplied by 2. multiplied by 2. Okay? Not multiplied by 2. You remember that. So that's it. So we have f of x of 1, we have this given. So the integral is equal to 0.2 over 3, and then f of x of 0 is 0.2. So basically the first term, and then everything in between, but remember that this is an alternate. So this will be just multiplied by 1, multiplied by 4, multiplied by 2, multiplied by 4, and then 1. So as you can see, this is a pattern that will continue. And just remember that the last term will always be 1, whatever. So it will alternate actually between 2, 4, 2, and so on if we have more than terms here. But since we terminated with x4, we have to terminate with 1. So it will alternate. Remember that this will alternate in between. That is just the shortcut to remember this. So we have 1.88 plus 3.464, and then plus 2 times, so f of x2 is 2.456, and then f of x4 plus 0.5. Okay, so the integral here, the approximate integral will be, I will calculate this more, but this is 1.6235. Okay, so this will be our approximate integral. As you can see, this is very much closer. This is the closest we have since 1.6405. Okay, so the more n you use, the higher the n, the better the approximation. Okay, so that's it for this lectures. You guys again tuning class hopefully on Monday or different day, and or Tuesday, and let's have a recitation. Okay, so yeah, thank you guys, and see you again in class.